I guess if ever there was a situation where there was an individual who did not need an introduction to a group of people, this has to be that situation. But as you can guess, I'm going to give one anyway. Seymour Cray was born in Chippewa Falls, Wisconsin. I have the date, but not knowing the sensitivities, I'm going to refrain from mentioning it. He earned a BS degree in electrical engineering in 1950 and a Master of Science in Applied Mathematics in 1951, both from the University of Minnesota. From 1950 to 1957, Seymour worked for Engineering Research Associates in St. Paul, Minnesota. His responsibilities included the 1101 and 1103 systems. In 1957, Seymour was one of the founders of Control Data Corporation, and while there he was responsible for the design of the 1604, 6600, and 7600 systems. In 1972, Seymour founded Cray Research Incorporated, and as I'm sure we all know, he's been responsible for the design of the Cray 1, the Cray 2, and the Cray 3 systems. This is a photograph that I made about 1970. The name on the mailbox is S.R. Cray. One of the streets there on the street sign is Data Drive. I wanted to make some contrasts. In 1970, a major portion of the world's supercomputing power was just down the road from this mailbox. The major organizations interested in supercomputing were fairly limited, and some of those organizations included the Department of Energy Laboratories, of which Los Alamos is one, some of the aerospace companies, and the National Security Agency. You'll forgive me if I've left anyone out who was interested at this early date. Another thing that I'll note at this period in time was that I personally was an operating systems programmer on supercomputers, and it was very difficult for me to explain to my mother what I did for a living. As I'm sure you know, today, by contrast, about somewhere in the vicinity of 20 years later, we find that there are several hundred supercomputers scattered throughout the world. There are many organizations who are now using supercomputing to perform their activities. There is international publicity and interest in supercomputing. Supercomputing is one of the in subjects amongst computing people today. And again, by contrast, today every time I see my mother, she wants to know the performance characteristics of Seymour's latest machine. What we're witnessing is profound and fundamental in the way that society exists. Computing is assuming an equal role with the classical theory and experimentation as branches of science. And I think we'll continue to see this, and we're part of that, and it's an exciting thing to be part of. Many people believe today that the country that controls supercomputing technology is going to control a lot of other technologies in the future. There are at least two reasons for that. One is you have to be very sophisticated and very good to build a supercomputer in the first place. And once you have those supercomputers with the fundamental knowledge that we're obtaining in the sciences, we're getting better and better at simulating phenomena. And with the power of the machines that are becoming available to us today, we're able to do that in quite a satisfactory manner. I wanted to introduce Seymour in some way that illustrated his extremely significant contribution to this fundamental change in the way business is done. And coming from Los Alamos, the first thing that occurred to me was introducing Seymour as the Albert Einstein of supercomputing because of the intellectual activity that's involved in producing one of these machines. I discussed it with a group of computer people, Someone else suggested that perhaps I should say the Thomas Edison of supercomputing because of the practicality of the contribution that he's made and the energy that he's brought to this subject. And as you might guess, in any group of supercomputer or computer people, where that group is one, there is a smart aleck. And someone else made a suggestion that Seymour had pushed the limits of supercomputing beyond the point where anyone thought that they could be pushed, and therefore we should introduce him as the evil Knievel of supercomputing. I thought about that for a while and rejected the idea and decided not to mention it at this. At any rate, it is indeed a great pleasure for me to introduce the individual who is almost single-handedly responsible for the foresight, the energy that's gone into supercomputing, for the lead that the United States enjoys in this area. And we very much appreciate his agreeing to be here today. So, Seymour Cray.
Thank you, and good morning. My primary mission today is to tell you everything I know about building a computer out of gallium arsenide. Now, that won't take all the allotted time because I don't know that much. So I thought you might enjoy a 10-minute history of our business as I remember it. For me, it began on the street in front of University of Minnesota in the spring of 1951. I'd run out of money, needed a job. It wasn't my money, it was the government's money, because I went to school on a program for World War II veterans, and you just have so much and then you have to quit. So there I was. I didn't have much idea where I was going to go for a job. Actually, college recruitment at that time was not the advanced technology it is today. You had to find your own job. I thought I had good grades, but I had no job offer. So one of my instructors passed me and he said, "You found a job?" And I said, "No, I don't really know where to look." So he said, "Try the old glider factory in St. Paul." And I thought that was kind of strange, but since I didn't have any place else to look, I found the old glider factory. Well, what I didn't realize then was there were two groups in the United States attempting to build general-purpose computers. One of them was on the East Coast with Eckert and Mauchly. It was called UNIVAC, Universal Automatic Computer. Jay Presper was never really modest, and I thought he probably thought of that name. The other group was in St. Paul working in the glider factory, and this was John Parker and Bill Norris. Bill had just got out of the Navy, and he was trying to make a living on cost plus fixed fee work for the Navy. That's a hard road, as we all know, and it was then too, but they seemed to be doing all right, and they had about 100 people there. So I took a job. Well, I worked for about a week, not knowing what I was doing, as many of you probably remember. And then it occurred to me, none of these people know what they're doing either. I had read all the books in the library, which wasn't much. And I realized in talking to the other people that the blind were leading the blind, and I was as good as anyone. So I got my first assignment. and maybe assigned to work there by tasks. And the task I was assigned to was task 13. Well, task 13 was attempting to build a machine which was really quite a general purpose machine. And my job was to build pulse transformers. Well, that doesn't sound very impressive, but if any of you have read, I don't expect you to remember, vacuum tube era, there's a problem with electrons going through vacuums. You have to have a high voltage to get them there, and so you have to have a transformer to get the pulses back down to the grids of the next vacuum tubes. And so this was a critical element I was assigned to straight out of school. Well, I felt uniquely capable of doing this job because I had two powerful tools. First of all, when I studied applied mathematics at the University of Minnesota, the last course I took was in Laplace transforms. And I figured I could solve most any technical problem with Laplace transforms. The other tool I had was a circular slide rule. Now, I had the 10-inch model. Now, that's as big as circular slide rules were made. So I had the very top of the line in computing capability. Now, many of you are probably not familiar with slide rules. But I can tell you, if you had a circular one, you had some social problems in college. The reason was that almost everyone else had a straight stick slide rule. And they came in a nice leather case, almost always orange. And they had loops on the back so you could hang them on your belt. Those minorities of us that had circular slide rules, of course, couldn't hang them on our belts. So as you walked around the campus, people looked at you kind of funny in the engineering campus, and they thought, of course, you suppose he's really not an engineer. But here came the payoff, I thought, because I knew I had this powerful computing tool and a way to solve the problem, so I went right to work. And I made reams and reams of calculations for my pulse transformers. And sure enough, the Laplace transforms worked. I built a prototype. It worked, and task 13 went into production with my pulse transformers. So I felt quite smug. And then one day, when I felt I was caught up on my work, I decided to take a walk down the glider factory and see what else was going on. Now, this was a big building. It was 2 blocks long, 1 block wide, and 30 feet tall. There's a little story about that I should mention, too. Why in the world was a glider factory in St. Paul? Well, this was left over from the government in World War II. And it had to do with landing in France on D-Day. They glued together a bunch of wooden gliders, and they hung them together with ropes, and they pulled them over the channel with one airplane. There was an airplane shortage in those days. And so the idea was, after you pulled them over the channel, you could cut them all loose and they'd float down to France. And they actually were used at D-Day, but in a very minor way. But that was why the glider factory was there. Anyway, I digress. Walked down the glider factory, and I found that at the other end of the line, by now Navy projects were up in the 20s, because things moved fast in those days. This was just months later. And I found a much older engineer, and I asked him what he was doing, and lo and behold, he was making pulse transformers too. And I told him about how I made pulse transformers using Laplace transformers in my big 10-inch circular slide rule. And he smiled and he said, I know about Laplace transforms and I know about circular slide rules, but I don't use either one of those. He says, I use intuition. And I thought, wow, here's something new. He said, I've been doing this so long, I can pretty much guess how to do it. And so I just make a few this side and that side of what I think is optimum, and I try them, and it goes much faster than doing all that calculating. And so I put away my circular slide rule, and after that I used intuition. So that was my very first lesson. Well, Navy tasks moved on. Didn't take long. A year later, I was on another project. We began to worry about commercial applications. Well, had to have another name. Couldn't use Task 13 because that belongs to the Navy. So we converted it to binary, called it the 1101. And that's how the 1100 series got started. After that, we decided we'd just keep on going through 1102, 1103, etc. By the time we got to 1103, a year had gone by, and I was the project leader. I mean, the promotions were fast in those days. And so had technology. Just to remind you, Eckert and Mauchly were building computers with vacuum tubes, of course, because that's all there was for logic. But they were using mercury delay lines for their fast memory. You know, transducer at one end, transducer at the other, and hook them together, and every time it comes around, you can change it. Well, that wasn't really random access. And we felt so much smarter in St. Paul because we had Williams storage tubes. And they really were random access because you could address each bit on the surface of the cathode ray screen. So what I'm doing here is preparing you for gallium arsenide. I hope you understand this. But as we went along to 1103, there were gigantic steps forward in technology, particularly in memory, because the Williams storage tube had 1,024 words. That was very big, but people thought they needed an even bigger memory. And so for the 1103, we had new technology, magnetic core memory, and we had a huge memory, 4,096 words. So that was the beginning of serious computing in the sense that people began to think of this as perhaps a commercial machine. And so it began a marketing effort. Well, that caught the attention of a typewriter company called Remington Rand. And Remington Rand bought both Eckert Mauchly and Engineering Research Associates in St. Paul and made this big conglomerate. And things began moving even faster. We got more and more contracts. The Air Force had a contract. Navy had contracts. Pretty soon we had all the business we could handle. Just to make the story a little short, there was one interesting phase before moving on to transistors, and that was magnetic circuitry. This was a very interesting phase, but didn't last long. After vacuum tubes, there was a period in which the square hysteresis characteristics of molypermaline offered an opportunity to make high-speed digital circuits without using so many vacuum tubes. You still needed a few to make big power pulses, but then the power pulses went through these networks of magnetic circuits, and you got the gain from the square hysteresis characteristic of the metal. A wonderful product of the steel mills in the United States. Well, one of the things I'm most proud of is a patent I got at that point in time. Those of you who are familiar with patents should appreciate this. I got a patent for parallel magnetic circuitry. And the thing I'm proud of is what the patent examiner wrote on it. This was hard to believe then. It's even harder to believe now. He said there was no prior art. Fantastic. I'll always keep that patent. Anyway, it only lasted a couple of years. There's a few products delivered to the Navy, and then the transistor came along. Now, they weren't the kind we have today. They were made out of germanium. They were called surface barrier toasted transistors. I never understood the toasted part, but it must have had something to do with process. Anyway, they were very fragile electrically. Just look at them crooked and they burned out. But they were faster than the magnetic circuitry, and so I have to believe it was the wave of the future. Well, I went through a number of other projects there, including one called the Naval Tactical Data System, which was a monstrous project by any standards at that time for taking all the inputs for ships in the fleet and converting everything to digital form and displaying it. And it was a very successful program, but the company was getting too big for me, so I decided it was time to move on. So did Bill Norris, because he was having trouble with Remington Rand management. So we started a new company called Control Data. Well, there were about 4 of us that were involved initially in getting that started. One of them was Bill Drake, and I have to digress here a little bit to tell you about the blue sky laws at that time. There weren't any. And so Bill Drake parked his car about a block from the entrance to Engineering Research Associates, now Remington Rand, and he left the door open, and he had a clipboard. And as people went by, he'd say, "Psst, you want to buy some stock?" And the word got around, and a lot of people stopped in. I stopped in, too, and I gave him all the money I had, which was $5,000. And he raised $600,000, which was kind of unbelievable for open-door policy at that time. Anyway, that's the amount of money Control Data started with. So we got a little corner office in a warehouse in downtown Minneapolis, belonged to the Minneapolis Star and Tribune. Working conditions weren't good there because we had just an office for about 10 people, and the rest of it was all open area. It was filled with newsprint. Well, newsprint came in monster rolls that weighed about 2 tons. And they were piled in one side, and I had this little lab on the other side. I worked mostly at night, and there was this noise at night because there were little wooden blocks under these big rolls, and they keep slipping. And you could hear this slipping noise, and you knew if any one of them let go, there'd be this big roar, and they'd all roll across the room and smash me into the wall. So that was the problem at night. There was a problem during the day, too, because the propane trucks were running all the time, and you could hardly breathe in there. But anyway, that's how that company got started. There was one other interesting thing, too, economics. It really was a lesson to me because I was the one that decided we should make computers. Everybody else thought we should go into point-of-contact sale machines for Dayton's and Donaldson's and department stores. I said, no, all I know how to do is make computers, so I'll do that. But I knew it had to be very, very cheap because we didn't have much money. So I went to the local store, which was sort of the Radio Shack of that time, and I said, what's your cheapest transistor? And they found me one made by General Transistor, cost 37 cents. And I thought, great, I'll take all you have. And I went back and I tried to make a circuit out of these things. And they were characteristics of just all over the place, no two alike. But never mind, I had to do it. So I made a circuit that was very, very tolerant. And it worked. Diode transistor logic, it was called. Well, I went back and got some more. I kept stocking up, kept going back and getting more. And then one day, the economics came to me. A man appeared at the door. He was from General Transistor. He said, I'm sorry, but you can't have any more of those transistors. I thought he was going to say, now you can get a volume deal. He said, you can't have any more. Those are the fallouts from our line, and you've used them all. So now you're going to have to pay twice as much if you want to get any more. What a terrible revelation. But then it was too late, so I had to go ahead anyway, and I made a 1604 computer. Well, time went on, and there was a whole series of rapid evolutions in transistors. It was only about 2 or 3 years later, and the planar silicon transistor arrived on the scene. What a great invention. It didn't burn out as easy, faster, and so the 6600 got started. There was a whole evolution during the period of 1960s where transistors moved along very rapidly, machines got faster and faster, Then something terrible happened. The serial speed of things stopped. And everybody promised me things would get faster, but they didn't. Years went by. Anyway, continued to make machines. Memories got bigger. Company got bigger, got too big. So I had to leave and start again. I like to start over, keep doing it. Did it just this year. Anyway, started Cray Research, and at that point in time, I concluded transistors just aren't going to get faster fast enough. We've got to think of something new. There was a vector machine being made called a star, which I didn't do. But I thought, not a bad idea. Start a new company, let's try that. And so we began vector computing initially at the beginning of Cray Research. Well, so that lasted for a little while, lasted about 5 or 6 years, and they still weren't fast enough. Transistors weren't fast enough. And so we began talking about parallel machines and parallel vector machines. This is a real struggle, obviously, because what we're missing here is the serial speed you'd like to have. So I began to think about gallium arsenide in about 1979 or 80. It was the time of the Cray 2 development program. I thought, it's time for something new. I knew that gallium arsenide was being used in communications work, and they said they used it because it was faster than silicon. So I said, why can't we make computers out of this? Well, there was one company that was sort of interested in doing it. It was Rockwell, and they were doing some government work, digital gallium arsenide. Tried to make a deal with them, tried to get some circuits made, but after struggling for about a year, concluded it was premature. They just weren't ready to manufacture gallium arsenide circuits of the kind I needed. So I had to give up on that and made the Cray 2 computer out of silicon. And that was too bad because the effect of that was that the scalar performance of the Cray 2 didn't keep pace with the vector because of the relatively slow circuit speeds. So here comes the computer generation later, and I've been working for about 5 years now on the Cray 3 project, and here comes gallium arsenide for real. And so I want to give you my impressions of the potentials and the problems and where we are in terms of using gallium arsenide for logic. There's no way right now we can use it for memory. So the Cray 3 computer is a combination of gallium arsenide for the logic and silicon for the memory. Not as incompatible as you might think, because the way that we're using gallium arsenide, very primitive form. It's called diode transistor logic. It's the same as the 1604 was 20 or so years ago. The reasons are the same. Gallium arsenide circuits are quite unpredictable, very non-uniform, and so the arguments for very early silicon circuits are the same arguments today in the choice of configuration. What excites me about it is I know what happened during the 60s after this primitive form, and I certainly hope the same thing happens in gallium arsenide during the 80s and 90s, because it seems like the potential is there. But what I'm trying to say is I think we're on the front end of something using gallium arsenide for logic, because we're accomplishing a factor of 3 speed improvements serially using very primitive circuits compared to the silicon versions we're comparing against. Now, when you talk to research people about gallium arsenide and you ask them why are they faster than silicon, they talk about electron mobility. 3 times electron mobility, or perhaps they use a little bigger number. And I never quite understood electron mobility. I was thinking about something else, which is capacity. And the interesting thing to me was that gallium arsenide is an insulator. Silicon is a conductor. And so when you look at the integrated circuit design, you find you can work with much smaller capacitances on gallium arsenide because of its insulating property than you can on silicon, because you've got a conductor right next to it. And so I began a development program, which again is really interesting. In beginning the Cray 3 work, and it was just about 5 years ago, I went back to Rockwell, and again the interest was rather minimal, but the group of people there who were leaving, spinning off a new company called Gigabit Logic. When I talked to silicon people about integrated circuits, when I talked to Rockwell about gallium arsenide circuits, they all gave me a big book of rules. And one thing about people that develop circuits without knowing about computers is they make rules that makes it very hard to make computers. So when I talked to the people at Gigabit, they said, geez, we don't have any rules, we're just starting our company. So I guess you'll have to help us make some. And I smiled. Here was a blank piece of paper, and I really love blank paper. So we got started off working together, and I finally learned the basics of field effect transistors, insulating substrate, Schottky barrier diodes, which come for free in that business because all you need is a little metal on the surface and you got a diode. And so in a period of about 9 months, we put together very workable gallium arsenide circuits using exactly the same circuit that was used 20 years earlier in silicon for the 1604. So we're pretty well launched, and we've been working together now for a number of years, and we're in production at last. The interesting thing is, as I started looking for a second source for gallium arsenide, went around to all the bigger companies, and they all told me the same story. They said, we have such a big investment in silicon facilities, gallium arsenide just doesn't fit in. We really don't want to fool with it. So I thought, thank heaven for startup companies, or we never make any progress. And it's interesting, in our country, there are so many spin-offs with new ideas. I think it must be the greatest strength we have in a technology sense, because people who get unhappy with structure in companies can move on, start their own, take the big risks, and occasionally find a pot of gold. And I think that's just wonderful. So let me talk a little more now about the Cray 3 computer specifically, how it's implemented, what the promises seem to be, and what the problems are. I've got a few slides I'll show in a minute, not very many, but give you a little background. First of all, what is the potential here? Well, the claim is that the Cray 3 computer will be 12 times the computing power of the Cray 2. Now, I said it that way very carefully because those of you who don't believe in parallel computation in multiprocessor machines would have some question about that number. So I'll separate it for you. Seem to have a factor of 3 speed linearly for every processor, and we can have 4 times as many processors for the same dollar investment. So there's the factor of 12, and you can use it in your own mind however you like, but it seems to be quite significant in any case, because 12 is an awfully big number. So that seems to be the opportunity. Now, what are the problems? Well, gallium arsenide is pretty horrible to work with in a process sense. It has a lot of grain. It has different grain in all 3 dimensions. So it seems to have a 3-dimensional structure. That is a rectangular structure. Electrons flow one way in one direction, different in another direction, and different in a third direction. So you have to line up all your circuits to use the grain of the crystal. Well, that's kind of tough. You've got to be careful to get everything lined up right. But then it's worse than that, because it's sort of like getting potatoes. There's hard spots and soft spots and knots and eyes, and it's very hard right now to get basic material which doesn't have flaws in it. But getting better every year, and Gigabit seems to be getting pretty good stuff, and right now we're getting a 50% yield on our integrated circuits for the Cray 3. And that's good enough to make machines, and we hope that goes up to 60 or 70% before long. And then we will have accomplished our financial objectives of being very competitive. So that's pretty much the story in terms of the speed of the circuitry. In terms of other characteristics of the Cray 3, we're taking a little clue here from our brethren. You know, in Cray research we have competing groups. We have our letter group of designers and our number group of designers. We have the XYZ group and we have the 1, 2, 3 group. And I work with the 1, 2, 3 group, but the XYZ group has been doing pretty good lately. And they had more parallel structure in their machine than we did in the Cray 2. Dual access to common memory and different kinds of access structures that help. And so those are being incorporated into the Cray 3 as well. So we expect to see quite a significant increase in performance, and we hope that this will all happen next year. This is the year of the YMP first delivery. Hope next year will be the first year of the Cray 3 delivery. Oh, we've been so lucky to have these two groups, and they seem to go through history one foot in front of the other and stagger out. This was not planning. This was sheer luck, and it seems to be working pretty well so far, so we won't change our direction. Anyway, couldn't find a slide of the original Cray 1, but Cray 1S is pretty close. The reason to show it here is look and think for a moment about the numbers, because when I come to the last slide, I'm going to put them all together in a chart for you. But here is a single processor machine. Clock period is 12.5 nanoseconds. 80 MIPS is the hardware speed, and 160 megaflops. Here's the packaging. This module I think many of you have seen. You know, it takes two hands to hold it. It's pretty heavy. It's really two-dimensional in the sense that there is a very minimum of interconnection between the two boards and the two sides of the module. And I want to contrast that with the later modules, which are truly three-dimensional. The circuits here are packaged in a very conventional way, hermetically sealed, have leads you bend and poke through the board, 4 gates, silicon. Here we see the Cray 2. Now, this is the one I struggled with because I couldn't get fast enough parts to do what I wanted. Had to make do. Memory is really PC computer memory. As many of you know that have run programs that are memory limited. That's too bad, but you have to use what you could get. Likewise, the silicon circuitry. Not really much faster than Cray 1, but larger scale integration. So there was some progress, and in a vector sense, we achieved essentially the goal I wanted, which was 4 nanoseconds. Came close enough, and managed to get 4 processors in the machine at essentially the same cost as the Cray 1. It would allow for inflation in the period in between, keeping a fairly constant cost from machine to machine. Number of MIPS is up substantially because of the 4 processors and because of the clock rate. Likewise, megaflops. The really exciting thing here was to use liquid immersion cooling. When I first talked about liquid immersion cooling, everybody in the project laughed. In fact, they rolled in the aisles because everybody knew the boards would swell up and it just wouldn't work. Nevertheless, we needed something pretty dramatic because we weren't getting very far with cooling with metal conduction. With the densities one has to have, the speed goes up. So we tried it, and what do you know? The boards didn't swell up. Actually, it worked pretty good. And today, I believe that Cray 2 reliability is as good or better than most anything else you can find. And a lot of the reason for that is the liquid immersion cooling. There's very little temperature difference between the parts during warm-up and during normal operation. And so we have good temperature stability, and that's a real key to reliability in the long run. Now, notice the person standing here, because that person is going to appear next in the Cray 3 slides. Not the immediate one, but the following one. Same person, all right? This is the Cray 2 module. Now, I thought this was truly three-dimensional. It isn't a cube, not physically, but it's a cube electrically. Because if one counts the number of lines that are going in the X direction and the Y direction on the boards, the foil runs inside the printed circuit boards. You count those numbers, and then you count the jumpers that are going perpendicular to the board. You find that the populations in all three directions are nearly equal. And the preferred one, of course, is the one that goes vertically because it's so short. And so the machine was organized for the really critical transmission paths to be vertically through the module. There are 8 boards here. And so if you looked at it electrically and you counted the integrated circuit packages, it's 8 by 12 by 8. It's very close to a cube. So I was pleased with this, and with the liquid cooling, it seemed to work just great. And although the circuits were slow, we did the packaging job. That's how I felt about it. You notice that the logic levels per clock period is only 4, and tradition is 8. And that's where you find the scalar performance slipping with respect to vector. No point in slowing the vector down. You might as well do whatever you can. But this caused an imbalance between the scalar and vector performance, and it was strictly a function of the slow circuits. Here we see the same person in the Cray 3 computer. Now, here the clock period has dropped to 2 nanoseconds, but the level of logic is 8 again. So here is the dramatic increase in serial speed. It is essentially 3 times what we can do in silicon today with equal effort, equal teams. We're comparing 2 nanoseconds with 6 nanoseconds with the same amount of logic being done per clock period. We have 16 processors, so there's the other big factor of 4. And now the numbers are getting more zeros after them. We have 8,000 MIPS and 16,000 megaflops. And we have gallium arsenide, which is the key to the serial speed. Now the module is getting pretty tiny. It weighs 8 ounces, and it's practically solid metal. And I hope you can see that there is a 4x4 array of 1-inch circuit boards. These are stacked vertically. And this is very high density packaging compared to anything else we've attempted. And the reason is it has to be to go with the gallium arsenide. If you have a factor of 3 improvement in circuit speed, you have to reduce the linear dimensions by a factor of 3. That means reducing the volume by a factor of 27. And that's not easy. If you figure the volume of the electronic part of a Cray 3, 16 processors, 512 million words of memory, the whole thing is less than a cubic foot. The rest of that is all power supply and cooling support. But the challenge here is twofold. One challenge, of course, is to package the gallium arsenide circuits in a way that will fit in the structure. Well, most people who we talked to about packaging just cringed at the requirement here because there's no room for a package. We have to package bare die. This whole package is only a quarter of an inch thick, and it has 4 layers of boards, 4 sets of die. And in order to do that, not only do we have to package the die without, mount the die without a package, but we have to grind the die down thinner than they come from the foundry because there just isn't room for all that die material. That's the part most everybody couldn't believe. Wafers are usually processed around 25 mils thick, and we have to grind them down to 12 mils because we save half the space in the computer that way. And that seems pretty weird. But If we didn't do that, we'd have a module that was almost half an inch thick, and the whole thing would be slower by a significant factor. So we do terrible things to these little gallium arsenide die. We grind them down, then we bond great big gold posts onto them. Not little wires, but big gold posts, 3 mil diameter posts. The reason for that is the mechanical bonding of the die to the board is done with the same thing that makes the electrical connection. Namely, these gold posts go right through these little tiny boards and get crimped like a rivet, very soft gold rivets, and we bond them 16 die to each of those 1-inch boards. We have a total population of 1,024 fairly large-scale integrated circuits in this area of 4 by 4 by 1/4 of an inch. There are 4 of these modules in a Cray 3 processor, 4 by 4 by 1 inch. And that's a real advantage in the sense that the wires mostly disappear. And we have wires between them, but no big number. And so the path lengths have dropped by, indeed, a factor of 3 linearly. Typically, the average path is right around 1 inch. And that's dramatically reduced from anything that's been done before. The liquid flows right through these modules, not perpendicular, but longitudinally. Total path for the liquid is the 4 inches you see, because these modules, 200 of which make a 16 processor machine, are arranged in a circle around the top of the tank you saw. The liquid flows vertically right up through the module, goes around the die, and goes back down a supporting pipe between the octants in the machine. So total fluid travel is 4 inches, and velocity is 10 inches per second. Those numbers come out to be a very modest temperature increase over the surface, and it's quite comparable to the Cray 2 in terms of total delta T. So here we have 200 to 400 gates. 500 is the maximum that we can have in a package. Gallium arsenide circuits. 4 modules make a processor. 200 make a whole machine, including the memory. And the logic levels, if we take into account all the paths, average out to be 6, which is about the same as it has been with 8-level logic machines. Here is the overview of system performance in the machines that I've been working on. And what I want to point out here is the vertical scale is logarithmic. Horizontal scale is linear years. Well, those of you that plot things on log paper know it's very hard to make curves go upwards on log paper. So I'm very proud of the fact that there's an upward inflection where gallium arsenide comes on the scene between the Cray 2 and the Cray 3. This is a big increase. Cray 4 is a continuation of the Cray 3. We'll talk about that a little more in a minute. But it's evolutionary, and you see we go from 16,000 M-flops to 128,000 M-flops in a period of 4 years. So we think we're at the beginning of something with this technology, and there's quite a long ways to go, and we're going to go just as fast as we can. And that's MIPS, and again, see the big inflection. There's even a larger inflection here because in the Cray 2 we could only issue instructions every other clock period. Not enough levels of logic. Here we have enough levels of logic so we can issue every clock period, and so it makes that curve even steeper. Tell you just a little more about what's happening right now, and then if you have some questions, I'll be happy to make up answers for them. What has happened in the past year is that the Cray 3 program got up to the point of building prototype modules, which more or less worked, but as we looked at the production problem, we didn't have enough production engineering experience as the project was constituted in Chippewa Falls to address the robotics required to manufacture the machines in volume. Parts are so small, vertical jumpers that I talked about are invisible. I mean, you really can't see what you're doing. So hand assembly does not really look practical except in an experimental mode. Besides that, the population is very large. We have 12,000 of those vertical jumpers in that 4-inch area. And so we need automatic assembly equipment which manufactures the jumpers on site. On site here means within a couple of inches, and puts them in the board, cuts them off, does the whole thing. Well, let me describe the jumpers for a minute and you appreciate the problem. Jumper diameter is 4.8 mils. That's very tiny. It consists of 7 strands of beryllium copper wire that are gold plated. It's the bundle diameter I'm talking about, 4.8 mils. Well, what we have to do is we have to weld these every 32 mils and then grab the welds and untwist the bundle to make sort of a birdcage effect so that as the jumper is pulled through the board, the bird cages line up with the board barrels. We use the barrel of the board for one side of the connection, and 7 strands of wire all making contact with the barrel makes a high-quality connection. So the way this is done is with laser welding, laser cutting, but it's all done in a very, very tiny area. These are made by Hughes, these machines that we're getting, made by Hughes. They provide the mechanism for moving the wire. Coherent General is currently making the laser system so that this machine will take one of these modules with the boards loosely stacked and go on a platen, go into this machine, and this machine puts in 12,000 jumpers that it makes as it goes, does the whole thing without human intervention. So there's a challenging problem for robotics. We haven't got this running quite yet, but we have prototypes now that are coming online. We're very optimistic this will happen in the next couple of months. That has been pacing. And as I said, we had problems simply with the human resources to do this work in Chippewa Falls, so we moved the project to Colorado this summer. I've moved to Colorado Springs, finding out about mountains now. It's quite a lot different than the flatland in Wisconsin, and thoroughly enjoying it. One of the reasons that we picked Colorado Springs was that there's been sort of a recession there for 3 or 4 years. Primarily defense cutbacks, I believe. But there were thousands of technical people there unemployed, and they didn't move away. They liked Colorado Springs, and they stayed there, pumping gas or whatever. And so when we moved into town, we didn't run an ad, but the local paper printed our picture, and we had 3,500 applications. It was wonderful. The real challenge was trying to process all those people to make the best possible choices. It was a very pleasant experience, so pleased with the move. There was some time lost with the move. As I view it, we lost 3 months in moving from Wisconsin to Colorado. But the additional resources we have now are several-fold what we had in Wisconsin. So I believe we have closed the gap, so to speak, on the move. I think we lost another 3 months related to plateauing without having the facility in Chippewa. So in my mind, this project has slipped about 6 months since we originally envisioned it. We were originally planning to deliver machines in the second quarter of 1989. It looks now like we'll deliver them in the fourth quarter of 89. But we're gearing up for production, so we hope to have a steep front end when we start delivering them. So, thank you, and are there any questions?
Could I start with a question?
Please.
My name is Jim Almond. I'm from the University of Texas Systems Center for High Performance Computing. Maybe I could begin the question with a reference to history, like you would understand. The 60-bit word length on the control data machines caused quite a little bit of problem and consternation migrating into the future, and now we enjoy a 64-bit word length. I have two questions about it. We're trying to establish teamwork between large-scale computers and scientific workstations. They also offer 64-bit words, but usually according to an IEEE standard for the structure of a floating point word. Is there any chance that we can enjoy a mainstream floating point word structure according to the IEEE standard on our large-scale computers? Is the first question. The second one is, many of our users seem to think that even a 64-bit word may not be sufficient for the accuracy we need in the future. How about even longer mantissa lengths in the future?
We certainly make a lot of compromises as we build machines, and I have a very difficult time in choosing the parameters that you're talking about. What I have done in the past is talk to that group of users of Cray machines who take their early machines, because I have to have the feedback soon, and ask them what they want. It was very difficult going from 60 to 64 for me, because everything I had done had been 6-bit oriented up to that time. But it seemed very clear that I was tardy in making that adjustment. And so that one was easy, because everybody told me to do it. In terms of, and one's complement arithmetic too, you know, way back there, in engineering research, I was taught that arithmetic should be done one's complement. That was because it was so easy to make negative numbers. But I finally caught on to that one too. But in terms of finding the right combination between exponent and coefficient, we got started down this road just quite a long time ago, and I'm not hearing enough reasons to change it now. Now, it may very well be awkward, but I'm reluctant to make a change just because of history, our local history. Don't think in a technical sense we would gain much with a different format there. So I doubt if it will happen soon. I think we have to stick with what we have for at least another generation. Longer word lengths are a problem in terms of utility. Here again, there are a group of people who clearly would like not to use double precision. I mean, we can obviously do longer word lengths. But if you look at the total amount of work being done, there are at least an equal number of people that are quite insistent on having 32-bit words, because they can use their dollar investment so much more efficiently. And so it seems like, and it's hard to have these options all at once. There's a real sacrifice in performance when you put options on word length. So it seems like 64 is the best compromise between the voices I hear, if you understand my position.
My name is Jack Worlton from Los Alamos. I'm interested in the Cray 5. In particular, I'm interested in the physical dimensions of the Cray 5. Because if your cycle time is going down by a factor of 2 and your processor is going up by a factor of 4, you'll be up around 10 to the 12th floating point operations per second, and I'm interested in the size of such a device.
Yes, I wish I could answer that. I feel nervy enough talking about the Cray 4 right now. It is certainly going to be biological, right? We've got a few people working in that area. I hope they can do it in another 4 years. It's going to be quite a struggle. The Cray 4 has a 1 nanosecond clock period, but as the Cray 3 does, it has a 2-phase clock. By that I mean in the Cray 3, we have to lapse the data every nanosecond. Now, that's not much travel time, even if the circuits were infinitely fast. So in the Cray 4, we have only 500 picoseconds between latch times. So this is getting right down to where gallium arsenide is important. And beyond that, it's a little hard for me to envision. I do think we need another material by then.
You just mentioned other materials. Two questions. What do you think about indium phosphide and some of the other 3,5 compounds? And what about some of the things that lesser mortals like IBM have not been able to conquer, such as superconducting materials?
Well, indium phosphide certainly is the thing in communication now, and therefore one would expect it to be a next step in terms of electron mobility. But is electron mobility really the issue? And it isn't right now in gallium arsenide. It's the insulating property that has the greater advantage over silicon. One of the things that's happening, and particularly in the communication area, is that putting epitaxial layers of indium phosphide on silicon, which is fine for that purpose, but the capacitance goes right back up. And so as I look at epitaxial layers of better materials on silicon, I find the capacitance problem really negates it, and that's too bad. Superconducting materials, I don't see how to use. I mean, other people are exploring cooler things, and that's great. It doesn't seem to me I should try to do what other people are doing. I'm trying to find a unique path to make a unique contribution, and so it has to be a narrow one. And I think I've got all the nerve I can muster right now for the gallium arsenide.
Roger Hockney at University of Reading. The limitation on performance of many of the computer systems, particularly the Cray 2 actually, is the performance of memory. You've told us a lot about how the logic's been improved with gallium arsenide. Can you see or say anything about improvements of memory access speeds?
Yes. There is a big improvement in the Cray 3 over the Cray 2 because memory circuits are progressing very rapidly still today, and I hope they continue to. The Cray 2 used, at least the early ones, used dynamic memory parts, which were very slow, like 120 nanosecond access. And the Cray 3 uses static parts that are the same size, weren't available then, but are now, with a 20 nanosecond access time. So there's a dramatic increase in speed due to the rapid evolution of memory technology in silicon. So I think that the memory in the Cray 3 is keeping pace, and in fact we see fewer conflicts with a 16 processor Cray 3 than we did with the 4 processor Cray 2 because of that big increase in access time and cycle time of static memory parts.
Thank you.
Chris Norrie, Amdahl Corporation, Sunnyvale, California. You're on a very fast cycle time, and making machines smaller must help a lot of the problems. Nevertheless, one of the beasts you must struggle with is clock skew. How limiting is clock skew, and how do you overcome those problems?
And here's a real engineer, yes. People talk about clock skew and know what they're doing. Yes, clock skew, of course, is always a challenging problem, and it is the reason that we moved from a single-phase clock in the Cray 2 to a two-phase clock in the Cray 3. With a two-phase clock, you can use a wide clock pulse. In fact, it is half of the clock period. And so you pay the price of having twice as many latches with a two-phase system, but you have much broader clock tolerances because you can have overlapping then between the two phases of the clock. And the result is the clock skew has to be only slightly better in the Cray 3 than it does in the Cray 2. And with the gallium arsenide clock fan-out modules, we have much tighter control of the clock. So we seem to be in better shape, surprisingly, with twice the clock rate, but with the two-phase system. Now, with the Cray 4, we'll be pushing it again. We'll be pushing very hard, and clock skew will be very, very important. but I don't know enough about that yet to tell you how tough it is.
Thank you.
Burton Smith, Terra Computer Company. Have you caught any Colorado trout yet?
Pardon?
Have you had a chance to catch any Colorado trout yet? Colorado trout.
Oh, trout.
Trout fishing.
Well, I've been up in the mountains every weekend and walking along the stream, but I don't have a pole.
I'll hug you one.
Steve Wallach, Convex Computers. In the same vein as the skew, how do you debug a circuit that is so small when you put a probe on it, you tend to alter the capacitive structure of the circuit, and therefore you may lose exactly the thing you're trying to find?
Yes, and I'd like to answer that in two ways. How do we do it initially when we're debugging a machine, and how do we do it when the machine is assembled in the field? Because they are different problems, both serious problems. The way we do it in terms of development is we test the modules individually, and they're very big. They're a quarter of a processor each. We test them individually in a dry environment with what we call a pulse power supply. That is, power is turned on very briefly, like for a millisecond, and then is turned off for a long time so the module doesn't overheat. But this occurs repetitiously, and so one is able to run the circuits at high speed for a very brief time, but brief time being thousands of clock periods. And therefore, we can then mount these under a microscope, and we have micromanipulators to bring in probes, and we touch the ends of those 12,000 jumpers. And they give us a lot of information, too much in fact, because you can spend a career there with your micromanipulators looking at pictures. But with 10,000 ohm probes on a micromanipulator with coaxial leads coming off them, you can get quite good pictures, and we get typically 300 picosecond edge times into the oscilloscope that way, without really loading the circuit too much. The circuits are 50 ohm impedance load, so if you put a 10,000 ohm probe on it, it isn't bad. So that's how we do it in the development phase. In the application of doing maintenance in the field, what we do is simply induce or deduce from the external things 3 computers away. We have to deduce which module is bad, which isn't all that tough because the processors are largely bit-oriented, and we have to determine which quarter of the word is wrong and take the module out, and then you put it dry again and you do the pulse power supply testing. So that's the vehicle. If it weren't for the dry mode of operation, it would be very difficult indeed. Have we done it?
That's it.
Thank you very much.